Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. In our last episode, we walked through the three major scientific versions of the multiverse: the bubble universes of eternal inflation, the branching parallel realities of the many worlds interpretation, and the vast landscape of possible universes implied by string theory. Each of them emerges from well-tested physics. Each of them is taken seriously by credentialed researchers. And all three share the same deeply uncomfortable feature: the other universes they predict are forever beyond our ability to directly observe or confirm. Today, we're getting into the battle over what that means, whether the multiverse is a genuine scientific theory, a philosophical overreach, or something in between. And by the end of this episode, you'll understand why this debate isn't just about physics. It's about the deepest question science has ever faced about its own limits. The central scientific objection to the multiverse, and it's a serious one that comes from serious physicists, not from skeptics who haven't engaged with the ideas, is that it appears to violate one of the most fundamental principles of what makes a theory scientific rather than philosophical. The philosopher Karl Popper articulated this principle in the 20th century. For a claim to be scientific, it must be falsifiable. It must make specific predictions that could, at least in principle, be tested and proven wrong by observation or experiment. A theory that can accommodate any possible observation without being threatened by any of them isn't making scientific predictions. It's providing a framework that's immune to evidence, which is precisely the property we associate with non-scientific belief systems rather than science. The multiverse, in all three of its major versions, makes predictions about realities that are causally disconnected from ours, regions we can never observe, influence, or receive information from by any physical means. Critics, including prominent physicists like Paul Steinhardt, one of the original architects of inflation theory who later became one of its critics, and George Ellis and Joe Silk, who published a notable essay in Nature arguing that the multiverse threatened to push physics beyond the boundaries of science, contend that a theory whose central predictions are in principle unverifiable doesn't meet the standard of scientific testability. Like, subscribe, and hype the video, and let's hear the response from multiverse proponents, because it's more nuanced than most people expect. Multiverse proponents have a substantive response to the falsifiability objection, and it's worth taking seriously rather than dismissing. The response comes in two parts. The first part is historical. Science has repeatedly accepted the existence of things that couldn't be directly observed at the time they were theorized. Atoms were accepted as real entities long before any technology existed to directly image individual atoms. Neutrinos were theorized in 1930 and not directly detected until 1956, a 26-year gap between theoretical acceptance and experimental confirmation. Gravitational waves were predicted by Einstein's general relativity in 1916 and not directly detected until 2016, a century gap. The history of physics is full of cases where the mathematics strongly implied the existence of something that took decades or longer to directly confirm. Multiverse proponents argue that being currently undetectable is not the same as being in principle permanently undetectable, and that future theoretical developments might reveal indirect signatures we haven't thought of yet. The second part is more direct. Some versions of the multiverse do make indirect, testable predictions. Eternal inflation predicts that bubble universes could occasionally collide with each other, and that such collisions would leave specific patterns in the cosmic microwave background radiation, patterns that observatories have searched for and haven't found yet, but that future, more sensitive instruments could potentially detect or rule out. The many worlds interpretations predictions are more subtle, but some researchers have proposed that decoherence, the process by which quantum systems lose their quantum properties through interaction with their environment, might eventually be studied in ways that provide indirect support for or against it. One of the multiverse's strongest motivations was the fine-tuning problem, the seemingly unlikely precision of our universe's physical constants. But critics argue that invoking an infinite multiverse to explain fine-tuning is itself a form of giving up on explanation rather than providing one. The physicist Lee Smolin proposed an alternative called cosmological natural selection, the idea that universes reproduce through black holes, with each new universe inheriting slightly varied physical constants from its parent, and universes with constants that produce more black holes producing more offspring universes. Over many generations, this process would favor universes with constants tuned to produce lots of black holes, which somewhat coincidentally tend to also be universes that produce stars, heavy elements, and potentially life. It's a Darwinian framework applied to cosmology, and it's a genuine scientific alternative to the multiverse that makes specific, testable predictions about black hole formation rates. Other physicists argue that fine-tuning may simply be less extreme than it appears, that our current understanding of what values the constants could take is limited, and that a deeper theory of physics might reveal that the constants we observe are actually the only mathematically consistent values possible, making the apparent fine-tuning disappear as a mystery once the underlying theory is understood. This is a hope rather than a confirmed result, but it's a scientifically respectable one. Like, subscribe, and hype the video. And now let's get to the deepest question this entire debate raises. Here's the deepest issue raised by the multiverse debate, and it goes beyond physics into the philosophy of science itself. If there are infinitely many universes with all possible combinations of physical laws, then by definition, every possible observation we could ever make in our universe is consistent with the multiverse existing. A theory that's consistent with every possible observation is, in a technical sense, not making any predictions at all. It's describing a framework so vast that no observation within it could ever point away from it. Some physicists find this deeply troubling. Sabine Hossenfelder, a physicist who has written extensively and critically about the multiverse, argues that it represents a failure mode of theoretical physics, a situation where mathematical elegance and internal consistency have been prioritized over empirical testability, leading physicists to construct elaborate, unfalsifiable frameworks that feel profound but can never be confirmed or denied by experiment. Others argue that the question of whether the multiverse is science or philosophy is itself not the right frame, that the universe doesn't care whether its structure is convenient for scientific methodology, and that if the mathematics of our best physical theories keeps producing multiverse predictions, the honest response is to take those predictions seriously, rather than dismiss them because they make physics uncomfortable. This debate is live, unresolved, and genuinely important, not just for cosmology, but for what we think science is actually for. So here's where the multiverse debate genuinely stands as of today. The physics that generates multiverse predictions, cosmic inflation, quantum mechanics, string theory, is among the most rigorously tested and precisely confirmed frameworks in the history of science. The multiverse itself is what these frameworks imply when taken at face value, without adding extra assumptions to make the other universes go away. Whether the multiverse is genuinely scientific or represents a productive frontier that has temporarily outrun our ability to test it, is one of the most actively contested methodological debates in fundamental physics. Both sides of this debate contain thoughtful, credentialed physicists who have engaged seriously with the arguments and reached genuinely different conclusions about where the line between science and speculation should be drawn. What's clear is that the question of whether we live in a multiverse is one of the most profound questions human beings have ever asked, and that our ability to answer it, if we ever develop such an ability, would require either theoretical breakthroughs we can't currently foresee or experimental capabilities that go far beyond anything currently available to us. So here's the multiverse in full. 3 independent areas of physics keep producing it from 3 completely different directions. The other universes it predicts are causally disconnected from ours and may be permanently undetectable. The debate over whether that makes it science or philosophy is genuine, unresolved, and important. And the fine-tuning problem it was partly invoked to explain has serious alternative candidates that don't require infinite parallel realities. What the multiverse ultimately represents, in its most honest form, is the frontier of what human mathematics can reach beyond what human observation can confirm, a place where the equations go, pulling the imagination with them into territory that may be real or may be forever beyond knowing. If you've made it through both episodes, let me know in the comments whether you think the multiverse is real science or beautiful speculation. Like, subscribe, and hype the video, and I'll see you in the next one.